Capstone course presentations at Twin Valley High School. I'd like to thank everyone that was able to view our presentations today through the live stream. I would also like to take just a quick minute to thank the administration here at Twin Valley for support of the program and helping the students to get through it and to get to this point, as well as my colleagues, because they've all had a hand in helping the students as well. And I would like to thank the experts. There's a number of experts that have helped the teams, and there's also experts that are viewing this to provide feedback to the teams on the work that they've done, so I'd like to thank them as well. And lastly, I'd like to commend the students because they've worked extremely hard throughout the semester. They've been very flexible. Obviously, during the current conditions, they've accomplished everything that I've asked of them, and they've done a great job. So I'm going to turn it over to them, and they're going to introduce the presentations, and we'll begin with the first group.
Good afternoon, experts and spectators. Welcome and thank you for attending our 2020-2021 Engineering, Design, and Development Senior Presentations. The format of the day is that each group will present a 15 to 20-minute presentation. Then, the presentation jury should complete individual evaluations through a Google form that has been sent to you. Although this year may look a little different, we express our gratitude to the presentation jury for taking the time to evaluate and comment on our presentations and demonstrations. Now let's get into it. This past semester, my group of student engineers and myself have been working on innovating, planning, and designing a prototype to solve the problem of bike theft. This presentation will include how we defined our problem, justified our problem, and our final solution, construction, and testing. Let me introduce you to my team of hardworking peers. My name is Abby Thatcher. We have Addison Kinsey, Oliver Savage, Regan Spar, and Molly Stevens.
As a member of the cycling community, I have seen the impact of bike theft firsthand. Over 2 million bikes were stolen across North America in 2019 alone. And with bike theft rates steadily increasing and less than 5% of stolen bikes being returned to the original owners, bike theft has become a major issue in cities and urban areas. Because our time frame was limited to one semester, we created a Gantt chart to make sure we stayed on pace and met our key deadlines.
One of the first things we had to do was identify the users of our product. We identified people living in cities because of the large amount of bikes in cities, as well as the popularity of using bikes for transportation. We also identified police because of the expensive bikes that they use and the fact that they have to leave those bikes in order to perform their duties. We also chose college students because of the popularity of using bikes for transportation and exercise, and people in beach towns because of the amount of bikes in those towns. We also had to identify the buyers of our product. We identified nonprofit organizations because there are nonprofit organizations that exist that are trying to limit the bike theft problem, and they would be interested in buying the product in order to further their goals. We also chose eco-friendly companies because many eco-friendly companies encourage eco-friendliness in their employees, which can include encouraging their employees to bike to work instead of drive in order to cut down on pollution. And we chose city officials because they will see the problem of bike theft in their communities and want to work to fix it. We had to identify our market through geographic location, educational level, income, and age. For geographic location, we chose cities because bikes are used for transportation and exercise. For education level, we chose high school students up to working adults because bikes are used for transportation and exercise. And for income, we didn't really see any income that was necessary for our market. For age, we chose 15 to 62 because they'll be working and using bikes for transportation and exercise. One of the first things we did was send out a survey to people in the biking community. We received over 300 results. First, we wanted to find out who we were surveying. So we asked what type of cyclists they were, and we wanted to find out what type of community they were living in and what population size of that community was. We wanted to find out how often our surveyors were riding their bikes, as well as how often they lock up their bikes when they go out for a bike ride. When we asked them how big of a problem they think bike theft is in their community, the majority of the respondees said that they think it is a large problem, responding 7 or 8, which told us that it is a problem that people are seeing. We also wanted to know how many times each of them had their bikes stolen. The majority of them said none. But when we asked them if they had friends or family or colleagues that had bikes stolen, the majority of them responded that they do know someone that has had at least one bike stolen. Originally, we had been thinking about creating a bike lock for our solution, but we later decided to switch to a bike rack. For our problem justification, we decided that the target market is continuing to grow with organizations trying to push kids to get into biking, as well as increased bike sales during the lockdown and continuing pandemic. We would reach our market through city officials and these organizations, telling them about the problem and showing them that our solution can fix that problem.
When we began looking at the existing solutions and patents, we identified the 4 main areas we wanted to focus on. Those areas were cost, ease of use, durability, and security. We used those specifications and began to look for patents that met our criteria. Each of these patents met a majority of our specifications, but fell through in one of the 4 major categories. We also looked at solutions that were already on the market. Each of these designs met all of our durability, security, and ease of use requirements, but with starting costs of over $1,500, they failed to meet our target cost. After we had gathered existing patents and solutions, we created a similar solution matrix and graded each of the designs based on our specifications. Out of the solutions we found, the Madlocker received the most points, scoring 25 out of 27 points. We then began to brainstorm solutions based on our research. Many of our earlier brainstorms included variations of bike lockers that would fully enclose the bicycle. We continued our brainstorm by completing mind maps. At the center of our mind map, we put a bike locker and branched our ideas off of that. Some of our ideas included making each unit interconnect, fitting 2 bicycles per unit, and including a bicycle maintenance station. Once we had finished brainstorming, each team member created their own product concept. We then used our design specifications to create our decision matrix and weighed each specification on their importance. We used this matrix to grade each of the product concepts.
So now with all of our designs and research completed, we came up with our own concepts. And this first one here is by me and Molly. It was an open rack that utilized electromagnets because of their strength and their ease of use. And we started figuring out how everything would work in these concepts, and these would be the ones that we would complete our prototype based on.
This was my personal product concept. Initially, we were thinking about ways to save space, so my design is angled and secured using pin locks. After evaluating, we decided that locking each bike part individually would be too time-consuming for users.
This was my product concept. The idea with this one was to lock up each of the main components, the wheels and the frame, with one type of locking system while allowing for adjustability, but we decided that it was too difficult to use and too difficult to manufacture.
This was my product concept. It is a locking bike rack that features a track to align the tires, a front tire holder, and an adjustable padded hook. This product offered a secure design without the use of multiple complicated systems. This design was our highest scoring product concept with a score of 111.4 out of 125. When selecting our final solution, we considered existing solutions, our target market, and the results of our decision matrix. Ultimately, we decided to continue with product concept number 4 due to its simplicity and ease of use. We then reworked the design as a team and created a much more developed product concept, adding in the specifics of the locking mechanism.
Shown on the board is how you use our bike rack. You can see the bike is placed into the tire rail. There, the hook can be lowered onto the frame of the bike. Once it's on the frame of the bike, it can be locked into place. To unlock it, you must use a key to pull out the pin lock, and a button is used to activate the clamp system to then pull the hook back to the top of the center post. For our prototype, we reached out to multiple engineers, bike specialists, and cyclists to get feedback. The 6 were shown on the board. Chris Lamison's advice was to make sure our hook wouldn't drop too fast to damage the bike. We made sure that the weight of the clamp shell wasn't too heavy to accommodate this in our bike rack. Shirk's Bike Shop told us to make sure that the frame was deep enough that when the tires are deflated, it still cannot be removed. Also, to add a padding to the hook to make sure it didn't scratch the bike. Both of these things can be shown in our prototype. Lisa Roberts said our prototype exemplified a very secure and easy-to-use bike rack, and this positive feedback helped us know that we were on the right track with our prototype.
Moving into assemblies. Pictured on the screen is the CAD models for our 2 assemblies in the design, the hook and the post. This is the full assembly, which incorporates the hook lock system, the post, the I-beam, the tire rail, and the front tire holder. Here is a model of the hook shell assembly. Inside the transparent shell, you see the modified clamp. That was used along with the hook that was donated to us by Shirk's Bike Company. Moving on to the clamp shell. This was cut and built using the plasma cutter, then welded together. We used finger joints to fit the parts together to create a box shape surrounding the modified clamp. The shell was also made to fit the I-beam, hook, and button, which play important roles in the design because this is how the hook shifts up and down onto the bike. There were many battles with the weight of this shell, but once we built it using 1/8 inch steel, we had a functioning design. Once our CAD designs were complete, we recontacted our experts to get feedback on our computer designs. Greg Unger highlighted the importance of a strong center post base. We explained to Lisa Roberts that we were using a modified I-beam clamp in order to keep the hook from slipping down the beam. Warren Donor emphasized that the fasteners and bike lock used should be strong. If we were to manufacture our bike rack for the public, our hope would be to integrate a fingerprint lock, provides more security and less hassle for users.
So before we actually got into the construction of our prototype, we wanted to do a little fit test. And like Abby said, the most important part was really our shell and making sure everything fit together. So we were fortunate enough to have a 3D printer in our lab, and we 3D printed a copy of our shell, and we tested the fits on the I-beam, the screws, our little pin, and it all fit well together. So we were ready to begin constructing. A lot of our prototype was made out of sheet metal because we wanted it to last out in the elements. And right here you can see I was using a CNC plasma cutter because of its speed and its accuracy, and then clamping all the pieces together to be ready to tack weld them. Here's our clamp shell, and then we 3D printed the button because we wanted to make it exactly the shape and size and weight we wanted it to be. So we also 3D printed that for our final prototype. Here's the post, me welding there and then putting it all together. There's our bottom rail all welded together after we cut it out. And then the front tire holders. This is us beginning to put everything together and double check that everything would work the way it wanted, just because we had never tested it yet with the weights of everything to make sure it would hold up well. And then we're almost completed welding. And then here's our final assembly, all together, but not cleaned up or painted yet.
We ran 5 tests on our prototype to make sure that it fit all of our design criteria. Our first test was our timed operation test. We had 3 randomly selected volunteers try to lock up a bike and unlock a bike. We wanted them to do this in under 3 minutes. As you can see on the chart, only 1 person was able to do this. Although all of our volunteers were able to lock up the bike, they failed to figure out how to pull the hook back to the top of the center post. We decided that if we were to do this again, we would add instructions on the side of the center post or make the button clearer to see so that users could use it easier. We then did a different size frame test. One of our frames was 133 centimeters larger, and as you can see, both of them still fit into our bike rack and were not able to be removed. This achieved our qualification of our bike rack being versatile for most bike sizes. Our next test was our freezing weather test. We wanted to know that our bike rack would last out in the cold, so we left it outside for 18 hours with a temperature low of 32 degrees. Our bike rack still worked perfectly after this, so we know that it passed this test also. Our next test was our tire channel test. We tested this on 2 bikes. We had them both try to stand for 10 seconds. 10 seconds was because that's how long we estimate it would take for a user to get around and lower the hook. Both of them were able to pass this 3 times, so we know that it can accommodate bike sizes in the tire channel. And our last test was our thief test. For this, we had 3 volunteers attempt to remove the bike from the bike rack. We already knew that if you tried to unlock the front tire, you could drop the frame out. The board is representing what we would want to do to prevent that. So at this time, we asked them not to remove the front tire. We also asked them not to damage the bike, since most bike thefts aren't trying to resell a damaged bike. None of our participants were able to successfully remove the bike, so we know that it does a great job securing the bike. And then this is just a photo of our final solution with all of it put together and the board representing the tire blocker.
When we met with our experts, we received the feedback that we should try and shoot for a cost of $200 per unit. When we finished building it, our actual cost came out to $180.44, which is significantly less than what we expected. So we think we can sell this pretty easily.
So because this is a pretty big and high maintenance project, we kind of learned a lot doing it. One of the most big things was time management. With 5 people, we still had a lot of people on hand, but we still had a tough time fitting it all together in the class. And so we kind of learned how to manage our time and use skills and abilities we had to the best of our ability. Another thing was we actually had 1 student who was at home in this new world we're living in. So it was kind of interesting to experience that and deal with it, but still get everything done and have him as a big part of our team. And then the last one was working as a group. There were 5 people, and there were a lot of things to get done, and so it was kind of difficult, but also cool to use everybody's abilities and have everybody work together.
Of course, given more time and resources, there would be a few changes that we would make to our design. First, we would make the clamshell less weight to prevent any possible chance of the hook falling on the bike at a dangerous speed. As mentioned before, we would hope to integrate a different locking form that is more secure for users. Another change we would make would be to add more sufficient coating to the hook to make it more safe to sit on the bike without damaging it. We would also make the width and the length of the tire channel larger to accommodate all bike sizes. Lastly, as Molly mentioned, we would add a blocker to the side of the front tire so thieves cannot access the front tire release and remove the entire frame.
We would like to thank all of our experts, Shirk's Bike Shop, Brian Falcon, Lisa Roberts, Greg Unger, Chris Lamison, Warren Dorner, and John Smucker. Also our teachers, Mr. Joy, Mr. Bowman, and all of the tech department, and all of our test participants for their help on this project. We thank you for your time and hope you have a great day.
There we go. So now we're good. Good afternoon, everyone. My name is Andy Saltzman, and these are my partners, Gabriel Dinsdale, Malavika Nair, Kyle Haddock, and Kristen Gebhard. We are Sedulous Industries, and I would like to present you the cone shoot. So, first of all, I would like to highlight a couple things in my problem statement. So in 2018 alone, 56 workers were killed on the job, and also for 2 workers, on average, placing 1 mile of cones, it would take them 25 minutes. We'd like to lower both of these statistics with our device. So here's our Gantt chart. We use our Gantt chart to keep ourselves on task, on time, and yeah. We also use our engineering notebooks to write down stuff that we did every day. So here's our justification. When we were doing research, unfortunately, we found out that there was a misplacement of a cone once, and it resulted in the death of a child. A car swerved around the cone, and yeah. So so we found out that each cone weighed about 12 pounds, and if you were laying 2.5 miles of cones, you would be lifting about 2 to 3 tons of cones. And also this usually takes around 2 to 3 people to lay out them. So current inconveniences, this is currently a dangerous job. It's physically taxing on the workers. It's time consuming, and it takes a high quantity of people. So here's some cones on a road that we would like our device to mimic this, lay out each cone equal distance, and be able to put out a lot of cones. Here's my partner, Malavika, trying to put out some cones. As you can see, they're heavy, and it's hard to place. And once she gets to it, you can see, even though the video is sped up, it takes a while walking back and forth and placing the cones. So here are survey results. So we gave out a survey to people in our that work in with cones, and we found out that 37.5% said yes to this question. Have you or anybody you know been in dangerous situations because of arranging cones? This is still a large amount to be in danger, and we would like to lower that. Also, how long does it take in your knowledge, to place 1 mile of cones? And 50% said 10 to 20 minutes, which is pretty good. but also the other 50% said more than that. We'd like to get them to the lower side, which is 10 to 20 minutes. So here's a picture of our final project. So design specifications. So we had a list of specifications that we wanted our design to adhere to, and I will highlight a couple of them. So we would like it to require only one driver and one operator. We don't want either of them to be out on the road while placing cones. We want it to weigh less than 200 pounds, the device in the whole. Also, we would like it to attach to a full-size truck bed, and we would like the cones to sit upright on the concrete or wherever we're doing it, 95% of the time or more.
So once we defined our problem, we wanted to look at what solutions were currently out on the market. One of them we found was Xcone 2.0. The advantages of this was you didn't need someone on the back of the truck or on the ground. You only needed one person driving. It could also lay a lot of cones at once. However, you could only use it on a flatbed truck. It took a lot to set up, and it is pretty expensive, over $2,000. Another solution we saw was the automated cone laying vehicle. This has a lot of advantages. Again, it doesn't require someone on the back of the truck. It only requires someone in the truck. It can be programmed to lay cones at whatever distance. It can also lay them off to the side of the truck so that the truck doesn't have to drive down the middle of the road and possibly close both lanes while laying out cones. However, it's $2 to $5 million, so it's very impractical for a lot of businesses. So then we wanted to come up with our own solution to try and fix some of the problems we saw with the current solutions. So we started with some mind maps. Basically, we started with a central idea. In this one, we started with a conveyor belt and then branched out into other ideas. As you can see in the orange, you can see we kind of developed maybe a chute is what we were thinking in it, and just being able to put a cone in, and then some mechanism would be able to drop the cones at whatever time. And you can see in the gray, we kind of had an arm we were developing, similar to the Xcone 2.0, and then we had some various other ideas throughout here. Here's another mind map we did. In this one, we started with a cone and then again branched out and created some other ideas. So we took all the ideas from the concepts and developed them into a few different sketches. So in this one, the cone wheel, it was basically a wheel that would attach to the side of the truck. You would be able to stand in the truck and put a cone in it, and then it would rotate and just drop down the cone at whatever time you wanted it to. It had a lot of advantages, such as it would be on the side of the truck so you wouldn't have to drive down the center of the lane, and it could be programmed to be whatever distance you wanted the cones to be apart. This was another idea we had, the conveyor belt. It's essentially you put a cone on the conveyor belt, and the conveyor belt the cone rolled down the conveyor belt to the road when it would drop off. Again, the conveyor belt could be programmed so that they would be whatever distance you would need the cones to be apart, and it would still require someone to be in the back of the truck. Our third idea was the cone chute. Essentially put a cone in the top of the chute, and it would drop down, and there would be some mechanism inside it, and that would drop it at whatever given time you wanted it to. So after we came up with these concepts, we had to make a decision as which one we wanted to go with. So we used a decision matrix. At the end, the cone chute had the most fit our specifications the best. So we developed the cone chute a little more. In this sketch, you can see we had a frame where we would attach the frame into the hitch, and it would also go over the tailgate and attach into the bed of the truck to give more support. Once that is attached, we would attach the actual chute to it, and you could drop the cones through the top, and then there would be some type of mechanism in it that would hold the cones until you wanted them to drop out the bottom where they would land on the road. Same with this one, we kind of changed for our chute. Once we developed it more, we realized we wanted it to be kind of lightweight. So we just used some angle iron instead of sheet metal going all the way around, which lightened up our chute. And we refined our frame also. So once we got the basic design down, we had to figure out what mechanism we wanted in to drop the cones. So one of them that we were looking at is the claw. It essentially held the cones up, and then when we wanted it to drop, it would turn and hold the other cones up while the bottom one fell out. And then it would repeat that motion over and over again, as you can see in the video. The other idea we had was the piston, which basically two pieces of metal. The bottom one would hold all the cones. When the bottom one came out, the red piece would go in and hold the rest of the cones up while the bottom cone dropped out. This would be controlled by the piston, as you can see in this video, and it would just repeat this motion over and over again. We ended up choosing the piston just because we believed it would be easier to control with programming.
As my teammates were saying earlier, we are student engineers, which means we needed a lot of help when it came to so we did consult with an amazing group of experts, the first of which was Dr. Marshall Coyle. Dr. Coyle works at Penn State, and he was concerned that the speed of the truck would cause the cones to fall over. We did refine some of the building and some of the construction plans we had in accordance with this. Mrs. Carrie Fisher is a Twin Valley alumni. She liked our idea, but she wanted us to make sure that the edges of our cone chute were not too sharp as to hurt people, and we did take that into account. Mr. Leaf Malm is another Twin Valley alumni. He liked the hitch connections and wanted to make sure that they would fit all trucks, not just the truck we were working with. And he liked the idea of adding stacks of cones rather than one cone at a time to reduce the physical capabilities you would need. Justina Wentling works within the traffic industry, so she gave us a lot of tips on how to deal with rules and regulations in places other than just Pennsylvania, which is where we were focusing our research. With her help, we were able to refine our model to make it more suitable for roads all over the country. And our electrical expert was Mr. Pradeep Prabhakar, who is an engineer. He recommended that we use a Raspberry Pi for any programming that we use, just so that there would be less wiring and it would be easier to code with. And that brings me to programming. As Gabe was saying, we did end up going with the piston, which means we needed to set a program to make the pistons go in and out. The first problem was choosing a computer. We were debating between the Raspberry Pi and the Arduino. The Raspberry Pi is a computer in its own, and it is wireless, so we would need a lot less equipment to deal with it. Whereas an Arduino is a microcontroller, which just makes it a little bit harder to work with. And the Raspberry Pi had a lot more of the aspects we were looking for. That, in accordance with the feedback we got from Pradeep Prabhakar, helped us choose the Raspberry Pi. The next challenge with programming was learning how to code. We used Python, which is a standard to use with a Raspberry Pi. To learn to code, we used a program called Thonny. This is the icon for that program, and the code on your right here is a code for a light bulb simulation, which I will show you in a minute. Because we were doing the programming in unison with the construction of the cone chute, we did not have the cone chute to fit the program to right away. So instead, I coded a light bulb, which would simulate the cones dropping in and out, which you can see with the light blinking. And we did connect our final circuit to the 12-volt supply in the truck. So as you can see over here, we used a 12-volt battery to simulate the truck because, again, we did not have the truck or the cone chute. This is a general plan for our circuit. So we had a Raspberry Pi, a relay, which is kind of like a switch, a battery, and once we had all of these pieces together, we soldered it together to make our final circuit. This is our final circuit. As I said before, we did use the truck's 12-volt supply, which is this connection that you see here. We used a buck converter to convert the 12 volts from the truck to the 5 volts, which is standard for a Raspberry Pi. As you can see right here, this is the Raspberry Pi. And then we used a two-way switch because we have pistons on either side of our chute, and this just made it easier to control everything. This is our final code. So we can set up the distance, we can set up the time between each piston and how in unison they are. And then this is us running the program. So at the bottom, if you can see that, at the bottom you would type in the project, and then it'll ask you for your tire radius. Once you type that in, it'll ask you for the truck speed. It will ask you for the distance you want the cones, and then once you hit Y, it'll start dropping. And then to stop it, you hit Q for quit. And then attaching the circuit to the chute is as follows. We took our circuit and we connected it to the 12-volt supply in the car. We did toy with the idea of using the hitch receiver. Unfortunately, the hitch receiver does not have a steady amperage, which makes this hard. And then we connected it with the chute in the back.
All right, so as we went into more of the designing phase of the actual chute itself, we started with our CAD modeling. So this is an overall model of just the chute in the back, and I'll get into that. We kind of split them up just to save weight. So on the left here, you can see your back frame, which is what can be mounted to the truck, and that's what's actually going to hold it onto the truck. And then it makes it a little bit easier to put it on since it'll be a less weight, and then also you could drive around with it since it's not as long. And then on the right is the actual chute that drops the machine, or drops the cones. So then this is just our overall dimensions of the actual chute itself. We went into 3D printing our machine just to see how the front would connect to the back. And then we went into a mock-up. Now it was a 1-to-1 scale, so it would allow us to see how everything would move, see if the cones would actually fit in the machine and all of that. One thing we realized with this is there was definitely going to be a lot of friction with our linkage and with the plate since it's all just steel. So we went in and we added a bearing in there just to kind of cut down on a little bit of that. So then next we went into our actual construction of the machine. First thing we did was to see if it was possible to even lift the cones up onto the machine. So we used a bucket for the height, and that's what it would be if you're standing in the truck bed and if you're going to lift it into the machine. And then, as you can see here, Malavik and Kristen cut pretty much all of our material for us since, as I said, all of it was metal. So we had to cut it all out on the horizontal bandsaw. And then we had to weld it all together. So the picture in the middle is one of our lower frames. That's just what kind of holds those traps on there to make them slide in and out. And then on the right is our back frame, just as I said before, to hold on the machine. So then we used, for the traps and the separation and the linkage pieces, we used a plasma cutter. And that was it was a lot easier than cutting out by hand. It was more accurate, and it just went a lot quicker. So then, as you can see here, here's our final pieces. We have the bearings in there, and then also the little piece of angle iron on that top separation piece is just so it can be mounted to the actual piston itself. And then for our dowel rods to go into the linkage pieces, we had to sand them down just so our tolerances would fit in there a little bit better. And then to make it easier to pull it on and off, we bolted the main machine onto the back frame. And then it takes roughly about 5 minutes to attach the whole thing to your truck. So first you would take the back frame, put it into the hitch, and it would just be held in by a regular pin. You would take this piece that would give support onto the bed itself, and then that would just slip right into the back, another pin in the top. And then last thing we would do, just to give it more support, is throw a ratchet strap over top, so it would kind of keep it down in the truck bed and give more support holding back. And then this is where we would need 2 people. One person would hold the main machine on there, and the other person would bolt it on. And we put 4 bolts, just 2 on the top, 2 on the bottom, make sure it was a secure connection. And into testing.
All right, so once we got our product made, we had to make sure that our testing fit our design specifications. One of our tests was our cone dropping upright. We wanted to make sure that out of the machine, the cone would land on its feet at least 95% of the time, and as you can see in the picture, they have landed upright. Another one of our tests was our mechanism durability test. So we had to make sure that our product would work and make sure that it would be reliable and function 100% of the time. Another one of our tests was our programming test. We had to make sure that it would, so as you can see, Malaviga is measuring to make sure that our distances are correct with the speed limit of our thing. Another one of our tests was a weight test. We wanted it to be under 200 pounds, and as you can see, it is 139 pounds, so it passed our test. Our labor test was how easily, how easily we could put the machine onto our truck. Like Kyle said, it only took 2 people. Our safety test was with our expert advice from Carrie Fisher, so we wanted to make sure that it wouldn't cut anybody. So we ran a piece of paper over it to make sure that it wouldn't cut the paper. Our grease test, we wanted to make sure that all moving components of our product could be greased within 10 minutes, and it passed that test. We did a road surface test to make sure that it would function on both gravel and pavement, and as you can see, it does work. And then our big thing was our pricing, because every single existing product was very pricey. We wanted to make sure that it was under $600 for the user. And as you can see, we have all of our components up on there with the pricing of everything. And it ended up being $455.41. So that passed our test.
Of course, with more time, we took a bit of our time to reflect and review on what we did. And with more time, there are some aspects we would alter. We would make a container for the circuit so that it's not exposed to the elements. We would have the chute pick up the cones as well. As of now, we're only doing half the job. It's still physically taxing to pick up the cones, so that is something we would look into. We would find a way to place the chute on one side of the truck so that we wouldn't have to close 2 lanes to operate the machine. We wouldn't have a linkage to move the plates. It just caused too much friction and was too much variability, which is why some of our earlier tests did fail. And we would add guides on the splitter and trap. As you saw with the mechanism durability test, our top plate tends to bounce up a little. Adding these guides would stop that. We learned a lot of skills and techniques. We learned how to work cooperatively. There are 5 of us, and there was a lot to be done. Dividing and conquering that took a lot of effort and took a lot of skills. And of course, we did learn how to use different tools. I learned how to use a soldering iron. Andy learned how to use a Raspberry Pi. Kristen learned how to use a horizontal bandsaw, as did Gabe, and Kyle learned how to use the welder. And of course, with any project, we would like to thank many people, specifically Mr. Michael Joy for being our instructor and seeing us through this process, along with all of the other technology education teachers, Mr. Paul Bowman, Mr. Adam Sanders, Mr. Courtney Moyer, our mechanical expert, Dr. Marshall Coyle, our civil expert, Mrs. Carrie Fisher, our electrical expert, Mr. Pradeep Prabhakar, our traffic expert, Mrs. Justina Wentling, and our engineering expert, Mr. Leaf Malm. We thank you so much for your time.
Hello everyone, I am Antonio Hall, and these are my teammates, Ethan Auger, Connor Lawler, Lauren Brown. We are LACE engineers, and we have created this Stella umbrella. Over the summer, we considered many different problems, but we decided we wanted to create an umbrella that's virtually impossible to get removed from the wind. We ended up with this problem statement. Poorly anchored beach umbrellas can cause injury when they blow out of the sand, and the owners of the beach can incur legal liability to someone's injury. 31,000 people were treated in hospitals for umbrella-related injuries from just 2008 to 2017, according to BBC. This is our team's Gantt chart. We used it to keep track of certain deadlines and to make sure our team was being productive with our time. Near the beginning of the year, we sent out a survey with overwhelming responses. Our target market was individuals who visit the beach yearly. As you can see, a large percentage of our respondents felt that they could be at risk from flying beach umbrellas. This clearly showed that we had a large market for our product. Then we looked into some existing solutions, and we found the Dig It umbrella attachment and this plastic umbrella holder. The Dig It umbrella is a shovel attachment that can be turned 90 degrees to anchor an umbrella once you have dug a hole. However, it takes a lot of effort to try to remove it from the sand. The plastic holder does have a quick pack-up time, but we wanted our innovation to be a part of the umbrella rather than just a holder. These are some of the patents we looked into, but none of them really fit our needs. This one is to the Dig It umbrella, and this one is just for a screw. Then we organized some of our ideas in this similar solution matrix. The blue tabs are our ideas for the canopy, and the white tabs are our ideas for the bottom half of the umbrella. We rated them on a scale of 1 to 5 based on 10 of our design specifications. Some of our specific design specifications were a 5-minute setup and a cost of $70 or less. Through this matrix, we were able to determine the features effective for the beach umbrella.
So after looking over the existing patents and what we had to work with, we began our own team sketching. And as you can see here, we started with 12 sketches. This is very preliminary sketching, and these were just kind of rough ideas that we had over a couple of minutes. And this was just to get the ball rolling, so we knew the path we were on and what we were going to use. Some of these ideas did make it all the way, which we have installed in the umbrella here, and a similar idea to the vents that we have up top labeled. Expanding on these, our team did brain sketches. These were longer and far more detail. After completing these sketches, we took turns passing them around in class, and this took about 1 hour to 2 hours. And these were really thorough sketches that really got our ideas down on paper and figured out what we wanted to do. And we figured out what worked, what didn't work, other things that we might want to add alongside the purpose of the umbrella. And we took these further in a couple steps. So before we made our final product concepts, we made a mind map. This one here is of the screw. We also have one of the canopy. So after we made this screw, we expanded on the ideas of what the materials could be, how we might design it, and other things. As you can see here, we have the ideas such as the 3 screws. We have the sand tarp, which we have on there. We can't cover with sand, but it's right there on the screen, that little red thing. So taking these ideas a little bit further, we made design concepts. These are more formal sketches that we had, and these took the sketches and added a product description to them as well as how they were operated. These are more formal sketches that we could send to our experts for feedback, and we included notes on how they should be used, what they might be made of, and things of that nature. Some of our feedback was good and bad, telling us things that we were doing right and other things we might want to take a look at, such as the Velcro. We had some ideas on the mind map, such as folding legs that would come out, which might drive up the cost or increase maintenance, and adding water into the pool, which we'll go into more detail later, which was all confirmed by engineers as well as beach resort owners. Similar to the summer solution matrix, we have the team decision matrix, which follows the same specifications. And these go into more detail about the ideas we thought about including into the umbrella, such as how we're going to do the canopy or how we were going to handle the base. Some of the ideas are listed here, and the ones we ended up settling on were the Holy Screw, which is a screw with holes in it for pouring down the water, sand base for covering the tarp with sand at the bottom, and Velcro venting. The umbrella up there at the top is 2 pieces, which comes apart with Velcro. So why this design? It's an intuitive design, just like any other beach umbrella. It is set up in a similar fashion. It's just much more sturdy and better suited at its job in staying in the ground. And this is in part due to the 2-part canopy, which I explained earlier, has the 2 parts at the top connected with Velcro. So if like a gust of wind comes along, instead of blowing off the umbrella or inverting the umbrella upwards and breaking it and rendering it useless for future use, the Velcro just comes off, and thanks to the ball up top, it stays on the umbrella and can be reclipped once the gust of wind is gone. There's a sand base, which lets you bury the base of the umbrella in sand, and that weighs down the umbrella. We have holes in the screw as well, and this lets you pour water down the actual pole of the umbrella, letting the water go down into the sand, making it a heavier paste. And this also creates a vacuum-like effect that we saw in the previous expert feedback slide. And as long as this functionality, this is just as important as staying in the ground, because if we had an umbrella that stayed in the ground but didn't do its job, it'd be useless. So we made sure it was a 7-foot diameter, providing plenty of shade for several people on the beach. And it's also highly durable. It'll last up One of our specifications was that it lasted 5 years, and thanks to the aluminum and the fabric material, it should last down the elements. And this is a quick video of how it works. All the parts that I explained, I'll go over real quick again. This is the time lapse of Antonio setting up the umbrella up at Marsh Creek, a local creek to us, with a small beach on it. So as you can see here, he screws it into the ground using the dowel and kicks sand onto the tarp. You can shovel or scoop it on however you like. And then he goes down to the lake, grabs water and pours it down, and that solidifies it like I said earlier. And then the top part of the umbrella just clips in and any other umbrella.
So before we could actually start building our umbrella, we had to model it on this 3D modeling software called Inventor. And if you're not familiar with Inventor, Inventor allows you to build, assemble, disassemble, and pretty much completely analyze your entire project. So you can see here on the left, we have our lower section, which has the screw or modified pole, as well as the dowel. And on the right, you have our umbrella sections. Again, here's this fully assembled version of our umbrella. And this is our working drawing for our umbrella canopy sections. So you can see we sort of had to improvise with Inventor. It's not necessarily meant to model fabric, but I think our team did well. You can see on the outside there's thick solid lines, and those would be the cut lines for our fabric sections. And then the dashed lines show the seam allowances. And finally here you see our screw. You can see a few important features of the screw are the notches along the side. That helps distribute the torques of screwing it into the sand along the entire pole. And you can see down in here we have our holes, and those holes allow the water to seep out into the sand. Before we could start building or sewing our Velcro sections onto our fabric, we had to research exactly how strong Velcro is. And we realized that there's actually 4 types of Velcro strengths. There's peel strength, shear strength, tension strength, and cycle life. And you can see in this little video here, we did with just a little bit of tape and paper that it shows that it was primarily shear strength that the Velcro would need, because you can see that it slips instead of tearing off in any other way. So from there, we were able to determine how much force would be on the umbrella from a max gust wind of 25 miles per hour. And it was pretty interesting, because the math that I used for that section, I literally had just learned a couple of days before in AP Physics. So it was pretty interesting to see how that physics, like my physics homework, applied to my engineering class. But from there, we were able to determine that we needed 1/2-inch lengths of Velcro to hold our umbrella together.
Okay, and then we got to start to build our screw. We used 3D printed plastic for our screws. These smaller screws are our test models. However, when we attached a pole piece to the model, it broke, even though we used sandpaper to sand it down beforehand. The blue and gray screws are the correct size. However, they were weak points in the 3D plastic, and some of the pieces chipped off. One of the features of our screw are these holes running down the screw. When a user pours water down the pole, the water exits the hole to create a vacuum between the screw and the wet sand. There are cuts along the top of the screw to help set the screw inside the pole, and these notches prevent the screw from sliding around once it is in the pole. This is our screw 3D printing, and this is Connor holding our final product. This is just a video to make sure that our screw would go through the sand easily.
So, like I said before, we ended up actually buying an umbrella frame, but with all of our extra parts that we added to our umbrella frame, including the screw, the umbrella skirt section, the fabric section on the bottom, and the handle, we had to make some modifications to our pole. So you can see on the left, I'm drilling, you see that thick drill bit, that was for our umbrella handle. And then the right side is I'm drilling some screws, or I'm drilling some holes for our screw section. Right here, you can see those little slots. Those would fit into the notches that were on the screw that Antonio talked about. and it was pretty exciting. Antonio, Ethan, and I learned how to use the milling machine, and we used some precision measurement tools on the milling machine. And that was a pretty good experience. It was very interesting. And here you can see our handle on the left side, and then on the right side is the hole for our handle. You can see we actually put a piece of PVC on the inside of our handle hole, and that was just to reinforce the section. When we were working with the pole, we realized that it just would be it wouldn't be strong enough to withstand the torques that would be put on it as you screwed it into the pole, or into the sand, sorry. So we put that piece of PVC in there just to distribute the forces along the entire length of the pole to increase durability.
After constructing the pole section of the umbrella, we were then able to move on to the canopy section. And like Connor had mentioned earlier, we did buy an umbrella to base our design off of. However, the canopy that came with that umbrella was just not fitting for our design. The fabric of that umbrella was not as lightweight or durable or weatherproof as we wanted. So we then settled on an Oxford polyester that was coated, so it was weatherproof. And we actually needed more fabric than the canopy had come to us with the original umbrella, because we needed to implement that overlapping section for that venting. So as you could see, actually in the last slide, there was that gap of space where the umbrella sections did not overlap. And then I luckily came up with a solution to fix that, where we added these 4-inch extension pieces to the top section of the umbrella. And after those extension pieces were on, we were able to sew the Velcro onto the umbrella. And the Velcro was inexpensive but durable and weatherproof, which was just what we wanted for our canopy. And once the Velcro was on, our canopy was complete. We were then able to move into the testing section, and the ergonomics were the first things that we decided to test. So here we have a student just carrying the umbrella in its bag, seeing how comfortable it was, and we weighed our umbrella in the bag. It came out to about 41.55 newtons, which is about just under 10 pounds, so it was perfectly comfortable. We also have some students walking around holding the umbrella. As you can see, it seems super comfortable, super easy to use. And we also have a student pouring water down the pole.
So while we were able to do our own testing at the beach for other purposes, earlier on in the project, we had to test the actual function of the umbrella. So here we have a student screwing in the umbrella into sand that's in a trash can. So it's not a perfect simulation. The trash can is much higher than the beach would be. Leverage isn't going to be the same, and there's not as much sand around it, providing the force. But as you can see, it's quite easy to screw in, even from that height. So this confirmed that our umbrella is going to be easy to install into the sand. Here's a table of the test that we just went over, and basically this is just showing that it's able to be transported easily, set up, and it weighs a comfortable amount, and everything passed, so this was satisfactory for us and confirmed that we were on the right path. Here's Connor at the beach, and this is when we were at Marsh Creek again, and he's pulling up with a force gauge on the umbrella. We clipped in the force gauge into just a little hole in the pole at the top, and after we installed the screw with the water and the sand trap at the bottom, he pulled up on it, and it actually exceeded the meter of about 100 pounds. So we know that for sure it'll be fine, as 100 pounds is way over than what we were looking for. And here's 2 more videos. See if the audio will play on this one. Yeah, so basically all I'll be saying,
guys,
or
been here for about an hour now.
saying,
Still no wind.
that's her nickname.
As you can see,
is that there's no wind, so we weren't actually
No
able to test the wind
ripples, no
functionality
wind,
of this. So we
but
made another video real
the
quick.
umbrella's looking
and
good.
this is just me pulling down hard on the umbrella to simulate a
guys,
gust of
been here
wind.
for about
And
an
as you
hour
can
now.
see, the
Still no
Velcro
wind.
top
As you can
comes
see,
off instead of the
all the
umbrella
water,
bending or
no
some other
ripples,
form of the
no
umbrella
wind,
failing.
but
And this again confirmed that the
umbrella's
wind is
looking
gonna,
good.
or the umbrella is going to stand up to the wind. And here's just another table again showing the force for both the sand base, the Velcro, and how hard it was to remove the screw by itself. And altogether, you can see that this comes out to roughly the 100 pounds that Connor showed on the meter.
From our cost analysis, we were able to determine that the umbrella would cost $89.88. So that was actually about $20 over our anticipated price of $70. However, if we were to take this into manufacturing, we could definitely purchase a lot of these items in bulk or purchase them in person, which would reduce the cost and hopefully bring us down closer to that $70 price range. In conclusion, a few things we would have wanted to change was beginning our construction earlier to allow for more time, focusing on those little details or little calculations that we might have missed. We would also like to weld rather than using bolts. Welding would just provide overall a cleaner look and it would be stronger. And then in addition to that, we would want to use buttons or magnets rather than Velcro. Buttons or magnets would also be stronger, and sometimes when you're pulling the umbrella in and out of its bag, the Velcro can detach, and those buttons or magnets would probably prevent that issue. And then again, in manufacturing, we would want to use injection molded plastic rather than the 3D printer for our screw. To reflect a few things that we learned, definitely time management, meeting those deadlines, and working punctually, staying on task. We definitely learned to work as a team better, cooperating, communicating with one another, and overall, I think we all learned a lot of new skills. I definitely improved on sewing. I know Connor, Ethan, and Antonio all improved on using the milling machine and other power tools. And lastly, we want to thank all of our teachers and our experts. We want to thank all of our tech ed department, especially Mr. Joy, who is our instructor for the course, and our experts, Tai Yo, Charles Krogh, Ben Fahm, Ben Cutler, Alex Ross, Bruce Hamlin, and Jared Lawler. We thank you very much for your time.
Hello everyone and welcome to our presentation. This is the telescopic weather shield. Our team is made up of Kate Olson, Sophia Marcello, Ben Johnson, and myself, Loren Rook. We are OMJR. The primary source of roof damage is hurricanes and tropical storms. Roofs are often damaged with holes as big as 2 feet in diameter, and smaller leaks leave the structure susceptible to water damage. On top of that, existing forms are all occurring on the top of the roof, which can be hazardous to set up. And when it comes to water damage, experts agree that for the first 24 to 48 hours, is critical for prevention of permanent damage and the growth of toxic microbes such as bacteria. So personal experience, about 2 years ago, my family had a trip to North Carolina when a hurricane hit and our attic fan was ripped off the top of the roof. Scrambling around to try to find a solution to try to plug this hole, which was letting tons of water through, we found an umbrella and had the idea to stick it through the hole. As this did prevent the water from kind of coming through the roof, it did have issues such as like it couldn't stay, tightly sealed and did let a little bit of water through, but this gave the inspiration to our idea. This is the final product. This idea was kind of formed on that kind of basis, but we created our own pole, our own clamps, and also our own anchor. Through this design, we are able to stick the umbrella through the hole or damaged roof, and you are able to unlock it. And the anchor and clamp is automatically connected to the underside of the roof and rafters. Water damage is more dangerous than you might think. Mold and bacteria grow exponentially over the first 24 to 48 hours, and that can be dangerous when the microbes and bacteria are released into the air and cause problems to people with underlying health issues. Loss of structural integrity is dangerous when beams and floors are submerged underwater, which can cause collapsing with the roofs and floors, and electrical damage occurs when the water is, connected to the electric damage and causes shock. This is our Gantt chart. We used this to manage our time and make sure that we met deadlines and kept each other on track. We made it into a couple different sections, such as defining the problem, problem justification, design, and prototype, and then eventually we got to testing. When we came up with our market, we wanted to make sure that it was a broad group of people, so we wanted to make sure we could make a solution for the biggest number of people. So we came up with homeowners. We asked over 160 homeowners, has your roof ever experienced any damage of any kind? And over 58.6% said yes. We then asked the market how long it took for a contractor or estimator to get out to the damage, and 72% said that they waited over 2 weeks. We then asked estimators and contractors how long they think it takes for them to get out to the damage, and over 80% said that it takes 2 to 3 weeks. And that surpasses our 24 to 48 hour critical time range for water damage. We then looked at existing patents. The first one is a tarp that is heat shrinkable to the hole, so that when it is placed over the hole, you can heat shrink it and it molds to the exact size. This is a type of shingle. It uses a photovoltaic electronic shield in between the shingles and creates a seal between the roof and the sheathing. Then we looked up the existing solutions that you can find in stores. We mostly found leak stoppers such as Flex Seal and Gorilla Glue. And we also found a small plug for small leaks, as well as tarps. All of these are installed through the top of the roof, which we wanted to make sure we avoided because that is very dangerous, especially in the midst of a storm. We then lined them all up and then tried to figure out which one was the best option. We found that the tarp is the best option for roof damage, but it is most dangerous as you have to climb on top of your roof, and especially during a storm, that is dangerous and causes a lot of deaths. We wanted to ask ourselves initial questions. Who are major competitors? As before, including tarps, our major competitors are Flex Seal and Gorilla Glue, but they cause a solution for smaller leaks, so if there was a big gaping hole in your roof, these could not help you. And then how we want to compare is we want to make sure that we are able to come up with a solution that was able to be installed underneath the roof, so you don't have to climb on top of the roof to make sure that it's secure. And by doing this, anybody could install this. There is no maximum age, income. Our intended buyers are all homeowners. We wanted to make sure that the solution is easy to be installed, easy to be secured tightly so that their water does not come through. And we wanted to make sure that there was no minimum age, income, education level, or location that this could be installed, that anybody could use it and it could be installed safely. When we came up with our design specs, we wanted to make sure that 90% of consumers could be able to fasten and secure this in under 5 minutes. We wanted it to be under 20 pounds so that anybody could be able to lift it over their heads, and it could cover up by a 3x3 foot area, which covered our 2-foot average. It needs to be waterproof, reusable, and must not protrude over 2 feet over your roof for curb appeal and also conductivity to lightning.
So one of the most important parts of the process for us was brainstorming. We wanted to make sure that we had as many possible solutions as we could down on a paper so that we could make sure we had the best solution possible for us. To do this, we used a bunch of different brainstorming strategies. The one you see on the screen is a brain sketch. Prior to this, each member of the team came up with 10 different unique ideas for solutions and chose one of these and drew a nice sketch on a clean piece of paper, which was passed around to all the group members who added notes, as you can see here, different sketches, stuff that they would change. And each one of us did a brain sketch, and after we did these, we talked about what we put down, sorted anything out that people had questions about, and were able to make improvements on the ideas that we had brain sketches for. This is another brain sketch. This would eventually become the idea that we would use. This is another one. This was a completely different turn from what we ended up doing. This would be prior to a storm, you would have this installed, and then if something were to happen, you would have it there. You can unroll it, and it's protecting the hole in your roof. Another strategy that we used was mind mapping. So for these, we start out with a central idea. Here you can see that preventative measure. And we would branch out with different ideas. It could be anything. It could be materials, mechanisms. As you can see here, this branch talks about mechanisms being mechanical instead of electric. This one talks about materials and functions of the actual tarp that would come down. And once we did all of that, we each settled on a design that we would focus on and created design concepts for all of those ideas. This would be our final design concept that we would use, and these are more detailed drawings. They have sketches of it being used, as you can see here, and different annotations and mechanisms inside of the actual concept. You can see here, this is the design concept for the preventative tarp. Here's another one that was a balloon type of design that would inflate to fill the hole and cover it. So around this time was when we started to get in contact with our experts. We relied heavily on Mr. Clark, Mr. Maynard, and Mr. Bennett, Mr. Keene, and Mr. Munger for advice on all different parts of the project. We stayed in contact with them all the way up through the entire process after we asked for their initial feedback on our concept sketches. The feedback could be anything from notes on our sketches, like you can see here, different things that they would add, to completely going over the sketch with us, and adding sketches or adding stuff to the sketches that they think should be included in our design. We also had a lot of Zoom meetings with them because we couldn't do those in person, and these are a lot of the notes we took looked a lot like this. This is notes from our working drawings that we submitted to one of them, and this was really helpful for us all the way up through the entire process. After we finished with our concepts and talked to our experts, we moved on to deciding on a final solution. We used another decision matrix for this and put each concept up against our specifications, and the one that we thought would eventually serve the best purpose was the umbrella style device, which scored 107, which is higher than either of the other two concepts that we used.
Okay, so after we determined that we wanted to further on with the umbrella concept, we proceeded to make working drawings for it and come up with exact dimensions and how it would specifically work. So that's what you're looking at here. Here's another sheet from our working drawings of the overall dimensions of our prototype. And here is an image of our final product. In this video, it will show how our prototype works. So here you can see you stick the umbrella up through the hole in your roof, and you push the telescoping poles up to open up the umbrella. You push up our anchor against the rafters or the roof, whichever works best. And then you use this, actually it's a bike clamp that we found to secure it in place. And then once that's locked in, then you can screw these bolts up to provide a tighter seal against the roof, which will ultimately keep out more water in the long run. This is the construction phase of our prototype. On the left here is a piece of sheet metal that we cut out on the plasma cutter. We use this for our central anchor, which was that component there that you saw had the bolts to make for a further tighten against the roof. On the right here is it more constructed. We drilled holes in the sides and threaded them, but we realized that the threads were not strong enough, so we added bolts to have more threads, so we welded those on there as well. Here's a video of the plasma cutter cutting out one of our parts. Okay, we use that for multiple parts throughout our construction process. Okay, so this was early on as we were building. We We're going to connect our umbrella, which we had bought at Target actually, and we were going to connect that to our telescoping poles through this washer that we were going to weld onto the poles and then weld onto the existing umbrella pole. But we soon found out that this was not going to provide a strong enough connection. So we proceeded by cutting off this washer here and going with a longer piece of metal to a tube and then connect to our existing umbrella pole. So here's us on the lathe, adjusting the radius of this piece of metal to fit into our tube nicely. Here's the lathe spinning our piece, just showing how that works. The lathe takes off little segments at a time to get down to your desired diameter. Okay, and then on the existing umbrella, and we line the umbrella with that to create a sealant on the edges. So when you're tightening the umbrella down, this half-inch foam layer would then compress against the roof and create a sealant against the shingles, because all shingles are different sizes and shapes. Providing this compression would ultimately keep water out. And here on the right is a picture of our prototype. Almost done, but we needed the anchor on there. Here is us folding our previous anchor on the brake. Starting off with our prototype, we had a straight piece of sheet metal for our anchor, but then we all decided that that was not going to be strong enough and it could warp as we were tightening it against the rafters. So we decided to fold it to provide more structural integrity. So here's us doing that. But then here is us spot welding more pieces in the middle to provide more strength again. And here's me welding on that piece that we cut down on the lathe into our umbrella pole. Okay, then when we proceeded to test our umbrella, once we first clipped it against our roof section that we made, we realized that the anchor was too heavy. So then we went back and we made some revisions and we made our anchor smaller and lighter, which turned out to really benefit the results of our telescopic weather shield.
All right, so due to our product being designed to keep water out, we had ran some tests, and most importantly, we ran this leak test, and we tightened our product against the makeshift roof, and we used a hose to simulate rainfall, and the test lasted 2 minutes, and which resulted in a total of 5 gallons being poured over the roof. And so in the first trial, you can see that there was a total of 1,400 milliliters of water that leaked through, and this was due to an insecure fit of the product on the roof. But as you can see in the second and third trials, there was a significantly less amount of water that leaked through, and this is all due to how tight you have the product against the roof. And our goal was to reach under 400 milliliters, which is about a pint. And here we have our weight and cost of our product. We wanted our product to be under 20 pounds, and as you can see, it added up to be around just about under 4 pounds, and the cost was about half of what we thought it would be. Our goal was to keep it under $100. And we had given out a survey to homeowners to determine the curbside appeal of our device. We asked them to rate it 1 through 5, and the majority of them gave us a 4 out of 5. And we also asked them if they would consider using our product if they had roof damage, and we also got an overwhelming majority saying yes. And then here we have our cost analysis, the total breakdown of the different parts and the quantity. And there were some lessons that we learned throughout the process. We learned that we can never have too much research on the market and the existing products to see what works and what won't work. We also needed to know the the interaction between the two different pieces, such as different metals. Some metals will corrode against each other, and then we also realized that with the two poles that there was some friction that was created when they slid against each other. And then we also needed to have a broad group of experts to expedite our brainstorming process and also our construction process. Some things that we would improve if we were to have more time, we would balance the weight out more, seeing that as it's an umbrella and most of it is metal, there's a lot of weight in the center, and it's hard to balance that out when you're putting it through the actual hole of the roof. And we would also create an anchor that with less friction between the poles and the anchor itself. And we'd also create stronger connection points between the poles so that it wouldn't be loose and have a better connection between the roof and the